Calculating the solubility using KSP. When you are asked to calculate the solubility of an ionic solid from the KSP, there are three distinct parts of the problem. 1. Writing the solubility reaction. 2. Writing the KSP expression. 3. Calculating the solubility. So here is the problem. Determine the solubility of silver phosphate in water. KSP for silver phosphate is 8.88 times 10 to the minus 17th. You are given the name of the ionic compound, silver phosphate, and the value of its KSP, 8.8 times 10 to the minus 17th. So the first thing we need to do is to write the correct solubility reaction. Writing the correct solubility reaction starts with writing the correct formula for the ionic compound, which we get from the two ions. In this case, the ions are Ag+, silver ion, and PO4 3-, phosphate ion. Because the silver is a +1 ion and the phosphate is a -3 ion, we need 3 silvers to match the charge of the phosphate. So the formula for silver phosphate is Ag3PO4. When we have a solubility equilibrium, the form of the reaction is always an ionic solid in the reactants and the separated aqueous ions in the products. So, since the compound is Ag3PO4, we start with that formula as a solid in the reactants. The products of the reaction are the aqueous ions of the compound, Ag+, the silver ion, and PO4 3-, the phosphate ion. To balance the equation, we need 3 silver ions. 2. Writing the KSP expression. Once we have the equilibrium reaction, it is easy to write the KSP expression. Remember 3 things. First, the general form of any equilibrium expression is concentrations of the products raised to the powers of their coefficients and multiplied together, divided by the concentrations of the reactants raised to the powers of their coefficients and multiplied together. Second, remember that this is one of the special equilibrium expressions that you should be able to recognize, with an ionic solid on one side and aqueous ions on the other side. The equilibrium constant will be KSP and will involve only the separated aqueous ions because, third, remember that solids and liquids do not change their concentrations and so do not appear in the equilibrium expression. So to write the KSP expression, we start with KSP equals. Then we put the concentration of Ag+, remember that square brackets indicate concentration, raised to the power 3, because the coefficient of the silver ion is 3, and multiplied by the concentration of PO4 3- raised to the power 1, because that is the implied coefficient of the phosphate. Calculating the solubility. Now that we have the equilibrium reaction and the equilibrium, that is the KSP expression, we can proceed to calculating the solubility of the silver phosphate. Since we do not know what the concentration of the solution will be, let's call it X. X, silver phosphate, dissolves. That is the solubility. Because the mole ratio between silver phosphate and the silver ions is 1:3, the concentration of the silver ions will be 3x. and the concentrations of the phosphate ions will just be X. Now we can substitute the variables we have determined for the concentrations of the ions into the equilibrium, that is the KSP expression. So, for the concentration of silver ions, we substitute 3X. Raised to the third power. Now, you may think we're using the 3 from the equation twice, and we are, but for two different reasons. The 3 in the exponent is there because the coefficient in the equilibrium reaction is the 3, and that's the way the equilibrium expression is written. On the other hand, the 3 of the 3X is there because we started with the solid. And when the solid dissolves, we get 3 silver ions for every silver phosphate that dissolves. If we do not start with the solid, then the amount of silver ion will not necessarily be 3X. So in this special circumstance, where we start with the solid, we will be using the coefficient twice, once in the exponent and once as a multiplier for X. Although there are other kinds of problems that involve solubility equilibria, this is all we will be doing for solubility. To finish the equation, we substitute X for the concentration of the phosphate ions. Now all that remains is to solve for X, since X is the solubility of silver phosphate. We substitute the value of KSP given in the problem and expand and combine the X terms. Expanding the parentheses 3X close parentheses cubed term can be a little tricky. You need to remember that when we cube the term, we cube each part of the term. This gives us 3 cubed times X cubed for the silver ion times X for the phosphate ion. This equals 27X to the 4th. Next, we divide both sides by 27, and we get 3.29 times 10 to the minus 18th equals X to the 4th. Taking the 4th root of both sides, we get X equals 4.26 times 10 to the minus 5th, which is the solubility of silver phosphate. If you are very comfortable with using the TI-80 series calculators to do this kind of calculation, you can stop the video now. If you want a little refresher instruction, here it is. There are a number of things to pay attention to here. First of all, you can enter the scientific notation either as it is normally written, like this, 8.88 times 10, little caret thingy, minus 17. The little caret thingy indicates that the minus 17th is the power of 10. Or you can use the enter the exponent button, EE, or perhaps EXP, to enter the power of 10, not the 10 itself, just the exponent, and it will look like this. This is the way the calculator will show the exponent after a calculation. Make sure that when you are entering the minus sign, you are using the sign change key, not the subtraction key. Next, to take the 4th root of a number, simply raise it to the 1/4 power like this. If you are entering the number in scientific notation, be sure to place the number in parentheses. Always place the power in parentheses as well. If you wanted to take the cube root, then the 3 would replace the 4 in the power parenthesis.